Okay, in this section, we're estimating a population mean. So that means, just like in the last section, we're going to be coming up with confidence intervals, but for a population mean, which we know that to be that Greek letter, lowercase mu. Okay. So recall a point estimate is a value of a statistic that estimates the value of a parameter. For example, the sample mean, which is denoted as x bar, is a point estimate of the population mean, which is mu. Okay. So let's start with a little small example here. It says, the following data represents the weights in grams of 17 randomly selected pennies minted after 1982. Estimate the population mean weight of pennies minted after 1982. Well, obviously we don't have access to the entire population data, so we have to estimate it by taking samples, which we have our sample here, and to find a point estimate for the population mean, that's just our sample mean, right, which is x bar. So if you run this through, let's put this in like L1 in our calculator. Each one of those we make a list. There'll be 17 different values. That's our sample size. We're going to calculate x bar using 1var stats. Okay. Again, the formula for x bar is just the sum of all our x values divided by the sample size. Okay. All right. So a confidence interval for the population mean is of the form, just like we had it for the proportion. Okay. We have a point estimate plus or minus the margin of error. In this case, our point estimate is x bar. Our margin of error is e. Now, this margin of error will be a little bit different than when we were dealing with proportions. Okay. Now, ideally, it would be x bar plus or minus some critical value times the standard deviation of x bar. If you recall from the previous chapter, we were talking about sampling distributions of x bar. The standard deviation of x bar was sigma over square root n. So that's where that's coming from, right? Now, I do say that we do not need to know this one. At least in my class, we're not going to be using this just because we don't typically know what the population standard deviation is. In practice, we probably don't know that. So we can't really use it, okay? Now, in some cases, there's you actually probably do know the population standard deviation, but not the population mean. But typically, you don't. Okay, so that's the first conflict. The second conflict is now that the sampling distribution will not be normal. Okay, because the sampling distribution of our sample standard deviation S is not normal. Okay. We have something that's a little weird that we haven't really talked about yet. Okay, so when the sigma is unknown, it is estimated from a sample standard deviation S, and the sampling distribution is what's called a student's t distribution. Okay, so what we have right here, we're using their normal distribution, a thing that's called the student's t distribution, or just t distribution for short. It's very similar to a normal distribution. Now, it's going to seem kind of complicated, but it really isn't. It's very similar to the normal distribution. All right, student's t distribution, or just t distribution for short. Suppose a random sample size n is taken from a population. If the population follows a normal distribution, the distribution of the statistic is t. Okay. Now, this might look a little familiar to you because normally we have something like, it's similar to the z. If you recall, z is like x bar minus mu over sigma over square root n. Now this is similar to that. Instead of the sigma, we're going to be using the sample standard deviation, okay? Because that's what we have access to. We don't typically know what the standard deviation is, the population standard deviation is. But if we have sample data, we can calculate the sample standard deviation. Now this distribution has a thing called degrees of freedom associated with it. Now for our class, we don't really need to know what degrees of freedom are in too much detail. It's not that important, at least for our understanding at this level of the course. just know that anytime you see the word degrees of freedom, it's just your sample size minus 1. So some of the properties of the t-distribution are as follows. Okay, the t-distribution is different for different degrees of freedom. Okay, so different degrees of freedom or different sample sizes give you different t-distributions. A t-distribution is centered at 0, just like the normal distribution, and it's symmetric about 0. Okay, the area under the curve is equal to 1, just like the normal distribution or any probability distribution. And it is also symmetrical, so to the left of and right of 0, the areas are 1/2. As t increases or decreases without bound, the graph approaches but never equals 0. So I guess it basically in the tails, it just asymptotically approaches 0. And the area in the tails of the t-distribution is a little greater than the areas in the tails for a standard normal distribution. So if you look at the picture here, the standard normal is what's in blue. So it's that distribution. Right here it's the tallest, but the height here isn't that important. What we're really looking here is the spread. So the normal distribution, if you look down at the very bottom, it's actually spread out less than all the other colors, right? The other two distributions are t-distributions, and they're different for different sample sizes. Okay, the smaller the sample size is, the fatter or the wider the standard deviation is. Okay, so there's a lot more variation in these t-distributions than there are in the normal distribution. Okay, so it's very similar to the normal distribution is what I'm trying to get at. Except for when we have smaller sample sizes, we typically have wider distributions. Okay, so let's talk a little bit about how to determine t-values. So just like inverse normal to find out the cutoff points, right? So if that's alpha, this is 1 minus alpha. It's the same thing for t-distributions, okay? Now on your calculator, if you have a TI-84, then your calculator does have this under bars, distributions, inverse t, just like you would find inverse normal, there's an inverse t. Now if you don't have a TI-84 and above, and you have a TI-83 plus, you won't have this function already native to your calculator. What you would have to do is find some sort of program that you can actually put onto your calculator. This is a very common one that people add to their TI-83s. If you were in my class, I would actually give you I would transfer over a program. But again, if you don't have access to me, then I will link below some of the online resources where you can actually put in values to come up with these critical values. Okay. All right, so let's go ahead and work an example here. Find the t-values given the area under the t-distribution. Area to the left of the t-value is 0.05 with n equals 15. All right, so for t-distributions and for z-distributions, to kind of come up with these t-values, we're going to draw a normal distribution curve or a t-distribution curve, which looks exactly like a normal distribution. It's bell-shaped, basically. At the center, you have t equals 0. And so I'm just doing that just to kind of center ourselves. And the area to the left of the particular t-value that we're looking for is 0.05. Okay, so how do we find that? Well, let me change colors here. We want the area to the left to be 5%. So, I mean, I know 0 cuts this distribution in half, 50% and 50%. But a t-value that would give you the left area of 5%, that should be somewhere around here, I would say, right? Where this area here is 0.05, right? And then the remaining portion would be 0.95, right? So this is that value that we're looking for. Okay. Now, how do you find this value in your calculator? Well, we need to come up with, this is going to be inverse, not normal, but inverse t. And the inputs are area to the left, and then degrees of freedom. Those are two inputs here. Okay. Now the area to the left in this particular case is 0.05. And the degrees of freedom, well, if the sample size is n, degrees of freedom is always n minus 1. In our case, n is 15 minus 1, that's 14. So that's what we put here, 14. All right, let's switch over to the calculator. So have the calculator on. Let's go ahead and go to second distribution. Look for inverse t. Area, they're referring to the area to the left, so it's 0.05. Degrees of freedom, 14. And let's go ahead and paste that onto our home screen. Press enter. And we should get a negative 1.76. So this is negative 1.76. And it does make sense that it's negative because it should be to the left of 0, so it does make sense that it's negative. Okay, let's do the next one here. It says, so they already drew a picture for us. The area to the right of the t value is 0.20, okay, with 10 degrees of freedom. Okay, we're looking to find that t.2. So this value here, well, that's going to be inverse t left area degrees of freedom. Okay, well, if this area is 0.20, what's the remaining portion to the left? Well, all of this should be 0.80, correct? So that gives us 0.80. And the degrees of freedom, well, they actually straight up give us the degrees of freedom. We don't have to do any subtraction here. So they just give us 10 to be the degrees of freedom. So sometimes it gave you either the sample size and you have to subtract 1 from that, or they might just give you the degrees of freedom straight up. Okay, let's put this into our calculator again. And if you round to 2 decimal places, you get something like 0.88. Right, so that number is 0.88. And again, it makes sense since it's a positive because at the center we have a 0. So it's a positive number. Okay, so just like before with the proportions, we're going to come up with the confidence interval for when we don't know what sigma is, when sigma is unknown. Okay, there's this bunch of criteria. Again, a lot of this criteria has to do with just obtaining the data with simple random sampling. Sample size is less than 5% or less than the population size. Now the data either has to come from a population that's normally distributed, or if you don't know that, your sample size has to be greater than 30. Now in all the problems that we're going to do, even if it doesn't mention that it's normally distributed and I don't have a sample size of greater than 30, just assume that it is normally distributed. Otherwise, we won't be able to continue pretty much the way that we want to. Okay, so constructing a confidence interval for mu with unknown sigma. So just like before, we're going to have some lower bound for the population mean and some upper bound, right? So that population mean is going to be between two numbers, right? Now our best point estimate for the population mean is the sample mean, right? And then we're going to have to add and subtract off the margin of error, which in this case, so there's the point estimate. This margin of error is related to what we talked about before, which is the standard deviation of the sample mean times the t-value. So it's giving you, in a way you can think of this as the number of standard deviations, okay? It's not exactly that interpretation, not like when we're dealing with z-scores, but for t-values it's similar to that. So here's the point estimate, margin of error. Okay, again, that margin of error could be denoted with just the letter E, and that's just this portion. And then to have a concise version of this confidence interval, it's x bar minus E and x bar plus E for the lower and the upper bounds. Okay, just like before, there is a calculator version of this. Before it was one prop z interval. This one's just going to be simply t interval. Okay. There also exists a z interval, and that's if you actually knew what sigma was. Okay, but we don't. All our problems are going to be where sigma is unknown. Okay, so we're only going to be using t interval. Okay. Again, there's an interpretation. So anytime we have our interval, we're going to be able to interpret that in the following way. We are whatever confidence level percent confident that the population mean, which is what we're looking for, of, again, the context of the problem will tell you what we're talking about, will lie between some lower bound and some upper bound. Okay. Now, note, as the level of confidence increases, the margin of error also increases. Okay, so if you want to be more confident in your interval, then you have to be willing to increase that interval wider, right? So that's what that means. The margin of error is just how wide it is. And the interval becomes, wider. So, / larger. Okay. As the sample size increases, the margin of error actually decreases. Okay. So with more data that you collect, this margin of error actually does get smaller. So it's worth collecting more data. And the interval becomes smaller / more narrow. All right, let's do a few examples. Example 3. Construct a 99% confidence interval about the population mean weight in grams of pennies minted after 1982. Okay, so what we have here is a bunch of raw data. Okay, raw data, these are weights of pennies. And we're looking for a 99% confidence interval for the population mean, right? That's mu. Okay, for a confidence interval for mu, that's mu. It's bounded between our lower bound and our upper bound, right? Our lower bound being our point estimate, which is x bar minus the margin of error, x bar plus the margin of error. Okay. Now, in this particular case, we can do it the long way, right? Where we have to come up with x bar, which is the sum of all the x values over n. Okay. And we can come up with the margin of error, right? Alpha over 2 s over square root of n. Now, either way, we can figure out, in order to figure out the sample mean, we have to actually collect all this data and calculate it, right? Same thing with the standard deviation, right? We would have to run this through our calculator, maybe through one of our stats to get this one. You can do that manually probably too, but finding S, you're going to have to use one of our stats to do it quickly. Okay. And then N is the sample size. You just have to count that. That's what I think 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? And to get the T here, well, it has to do with, well, we need to know what the area to the left is, and you need to know the degrees of freedom, and that's all doable. Okay. Now it's very tedious, and this is not really the way that we normally do it. The preferred way is just to use the TI calculator's function T interval, because you're going to be putting the data into your calculator anyway to calculate the mean and the standard deviation, and then putting all those pieces back together. And if you round too early in the problem, it does kind of screw up your final calculation. So just using the function in our calculator will be a lot more efficient. If we use a TI calculator, we're going to use the function T interval. Okay, we're going to have to put this list into our calculator also. I'll put this under L1. Okay, let's switch over to the calculator and see what we get. Okay, so recall that in order to put a list into your calculator, you got to go to Stat, Edit, clear out any lists that are there. I'm just going to go up there and clear. I'll just clear everything just so it's kind of out of the way. and just start typing away. Okay, so once you have your data in your list, I always suggest going over your data and just making sure everything is correct. It's very easy to mispunch a number and think it registered, and it actually didn't. Okay, so go ahead and go through that and check. Okay, so I've gone through my data and I've checked everything that's there. From here, I like to quit all the way out to the home screen. So you just go to 6-second quit. Go back to stat. Go to test. We're going to go down to T interval if you can find it. Now, what would be Z interval? Well, if we actually knew the sigma, the population standard deviation, we would use Z interval. But in this case, we're going to use T interval. Okay. Now, as you enter this menu, you're going to see two options at the very top where it says INPT, that's input. It can either be data or stats. So in our particular case here, we had raw data. We want to make sure that the data is highlighted. So right now stats is highlighted. So you want to move to the right, press enter over data. And then from there, now we can find the list that our data is in. My list was in L1. If yours was in any other list, let me just clear that out. Then you just type in L1, like Mike is L1, second one. Frequency list, just keep that at 1. It means that our list isn't being repeated or anything like that. And then the confidence level. Okay, in our particular case, we have a 99% confidence, so we have to put that in as a decimal, 0.99. And let's go ahead and calculate. Okay, so at the very top, you have your lower bound and your upper bound in parentheses, separated by a comma. And it also calculates the sample mean and the sample standard deviation. And it actually counts the number of values in our sample, which was 17. Okay, so mu, if we round to, let's go with 2 decimal places. I like to round usually to either the same amount of decimal places as our original data or at least one more. Let's do 2, just do 2. 2.45 and 2.48. Okay. Now again, the interpretation here is very similar to the proportion. We say that we are, in this case, 99% confident that the population mean, and then the context of the problem, weight of pennies minted after 1982 is between 2.45, this is measured in grams, grams, and 2.48 grams. Okay. The real interpretation is, if we were to do this 100 times, right, this interval that we get, 99% of those 100 will actually contain the true population mean. Okay. Only once will it be outside of that interval. Example 4. A simple random sample of size n is drawn from a population of size 1000. The sample mean is found to be 33.2. The sample standard deviation is found to be 7.9. Construct a 90% confidence interval for the population mean if the sample size is 45 and there are no outliers in the sample. Okay, let's address that first sentence. It says a simple random sample of size n, which we found for it to be 45, they said it at the very end, is drawn from a population that is of size 1000. Okay. Why did they give us that? Well, it's just to kind of go through one of those criteria. As long as your sample size is less than 5% of the population size, then we're good. Okay, so in this case, we actually are given statistics. We're not given raw data. We're given statistics. They give us the mean, sample standard deviation. They also give us the sample size and the confidence level. Okay. So we're looking for a confidence interval for the population mean. We're going to have some lower bound and some upper bound. And let's figure out what that is. Okay, so they give us the sample mean. In this case, it is 33.2. Sample standard deviation, 7.9. Fix that S. And the sample size is 45. Confidence level in our case is a 90% confidence interval, so 0.90. Again, let's switch over to the calculator. So again, we're going to go to the stat menu, go over to test, go over to T interval. This time, since they give us summary statistics, we're going to go over to the stat inputs. And then now they're asking for what's your X bar, so I'm going to clear everything out. We have 33.2. The S was 7.9. Your sample size was 45. Your confidence level in this case is 0.90. And we're going to go ahead and calculate. Just make sure I put everything in correctly. Looks good. All right. We have a lower bound of 31.221 and an upper bound of 35.179. Now, if you actually did want to have more decimal places for those, so for example, if your homework asked for more decimal places than those, now these values are stored in your calculator. I do want to show you where that's found. Okay, if you go to VARs, and then you go to statistics, and if you go down to, let's go all the way to test, and if you go all the way down, you're going to have all these variables that are stored in your calculator. And oops, I just messed it. You have your lower and your upper. If you wanted to find your lower value, just click on that and then press enter, and that gives you more decimal places than was already given to you on that one screen before. And the same thing with upper. Okay. All right. I'm going to round to just one decimal place for this problem. We're going to get 31.2 and 35.2. So the interpretation here is we are 90% confident that the population mean, they didn't really give us any context to the problem, right? It's just kind of it's an abstract problem. So we just say the population mean is between 31.2 and 35.2. There's really no units associated with this. It was just an abstract problem. Okay, this next part of this section is very similar to what we did in the previous section for proportions. If you're already given a lower bound and an upper bound, then we should be able to back into calculating the mean and the margin of error in the exact same fashion that we did it last time. Okay, so again, let's do that for this example. We're given a lower bound, we're given an upper bound, and it's asking to find the X bar and the margin of error. Okay, to find the sample mean here, it's just your upper bound plus lower bound over 2. Upper bound in this case is 150, lower bound is 100 divided by 2. We're going to get what? 250 divided by 2. That comes out to be what? 125? Okay, and that does look like it's at the center of that interval that we see between 100 and 125. The margin of error here is upper bound minus lower bound divided by 2. 150 minus 100 over 2 150 minus 100 is 50. And we get 25. Okay. Let's go ahead and check to see if that does match up with what we should expect it to be. The mean is bounded between x bar minus the margin of error, x bar plus the margin of error. In this case, the x bar is 125. The margin of error is 25. X bar is 125. The margin of error is 25. 125 minus 25 is 100. 125 plus 25 is 150. Yep, it does match. Okay, this next part has to do with determining what sample size you need in order to achieve some sort of margin of error. Okay, so this is all done before you conduct whatever survey of data that you're collecting. Okay. All right, so there's not only just one formula for this particular problem. Now, this does require you to actually know some sort of prior estimate of standard deviation. There's no way around it. Okay, this is the z-score, just like we know. We get this from the confidence level. Depending on what the confidence level is, we can look it up because it is a z-score. It's one of those typical ones. If it's a 90, a 95, or a 99, we can just look that up. And then the margin of error is usually given to you by the key word there is, if you look for the word within again. Okay, and then of course don't forget the square. Let's do an example. Dr. Dexter wants to estimate the mean serum HDL cholesterol points of all 20 to 29-year-old males. How many subjects are needed to estimate the mean serum HDL cholesterol of all 20 to 29-year-old males within 1.5 points? Okay, with 90% confidence. Assume the standard deviation of 12.5 points based on earlier studies. So they're giving us some prior studies standard deviation. That's our sigma. They're asking us to how many. Again, that's telling us we're looking for n. So that's telling me that I'm looking for a sample size. And to estimate the mean. So we know we're going to be using this version of it. Okay. So we have that z-score, standard deviation, margin of error, and then don't forget the square. So let's go ahead and catalog what we know. So z-score here, well, this comes from the confidence level, right? Our confidence level is what, 90%? So that tells us that our z-score here has to be that 1.645. If you don't know where I got that number, look at the previous section where we talked about how we got those. Okay. This is one of the common ones. So any confidence level that has to do with 90% when dealing with normal distributions, which in this case a z-score is a normal distribution, it'll be 1.645. Standard deviation was given to us as 12.5. And then the margin of error, in our case, they're saying we want this to be within 1.5 points. Okay, now it's just a simple matter of plugging this all in. We have 1.645 times sigma, 12.5, margin of error, 1.5. Then don't forget the square. Okay. If you calculate this, I'm going to round to 1.879. Now again, we always round up. So 187.9 should round up to 188. Always round up.